In this problem, we look at 14.A.4 from Pinter's book, which gives us the following situation. We have a piece of paper with vertices A, B, C, D. And we have talked at some great length now about, well, let's assume it's a square piece of paper, right? I know my drawing doesn't look very square, but it's a square. How to rearrange the vertices of this piece of paper using rigid motions. Pinter tells us to consider the side that is face up as side A, and the side that is face down is side B. And in particular, what he tells us is to realize that every motion of this square piece of paper either leaves the face up side face up, or it switches the face up side with the face down side. And in that way, he says that we obtain a function from D4, the collection of symmetries of the square, to S2, the symmetric group on two things, the permutations of two symbols, namely side A and side B, where the function goes, we send a group element to the identity of S2 if side A stays up. Doesn't have to be side A, the current side stays up. And we send a group element to the non-trivial transposition. Maybe in cycle notation, we'll just write AB if the sides are flipped. Right? That's good cycle notation for flipping the sides, so it seems reasonable. And these are the only two elements of S2, as it turns out. Right? You have two things, you can leave them alone or you can switch them. And so the question is to show that this is a homomorphism and also to see what the kernel is. Were there any other parts? Let me just go take a quick look. Verify it's a homomorphism, give its kernel. Nope, that was it. Okay, so to check that this is a homomorphism, we need to check what happens when you compose two elements. So, and we also have to see, oh, I guess I don't have to check that phi of E is E. If I check that it's a homomorphism, then I know that phi of E is E because that's a consequence. So in D4, we have seen every element is either a rotation or some kind of reflection. And an important observation from geometry is as follows. Compositions of reflections. Sorry, let's start with rotations. Compositions of rotations are rotations. Compositions of reflections are actually rotations. And compositions, one of each, are reflections. And if you're not completely sure about that, you don't remember why that might be the case, well, I invite you to go get a piece of paper or something that's roughly square shaped, a sticky note or something, and then try it and label the vertices and convince yourself that it's true, because I promise you that it is. While I've been yapping, you have gotten up and paused the video and done that if you wanted to, and now you believe me by the power of time travel. Okay, so with this in mind, we are quite close to concluding that this is a homomorphism, because in the process, you have probably also become convinced that the side flip happens exactly when you are a reflection. So reflections flip sides. rotations just turn the page. And so let's translate this into what happens with our function. We'll call our function phi. Phi of rotations is the same thing as phi of some specific rotation, which doesn't flip. E.g., it's the identity element. On the other hand, phi of two reflections is a rotation, which should be E. And if I calculate it a different way, I get phi of one reflection, followed by phi of another reflection. And each of those are flips. But in the symmetric group, any transposition squares to itself. So we see that in this case, this non-trivial equation holds, and we're happy. The last thing we have to do is consider what happens if I have one of each. This becomes phi of a rotation and phi of a reflection, which gives E times AB, right, from the reflection, which is AB. And using our geometry, we know that this is also a reflection, which gives the non-trivial permutation. So in each case, the equation is verified. The last thing we have to do is identify the kernel, and I've basically done that. I just didn't say it. The kernel is the set of things that map to the identity. And well, rotations simply turn the page and therefore do not flip the side. In other words, they map to the neutral element of S2. So the kernel of phi is exactly the rotations, which is isomorphic to Z mod 4Z. And maybe as a little bit of a extra little exercise, you can check that Z mod 4Z is normal on your own, because it's not that much work, right? The geometrical considerations that we've been making this whole problem are very, very close to finishing that problem for you, but a good sanity check for you.